Good evening, mathematicians and lay math enthusiasts. My name is Jeff Cook, and this is Greg Volk here. Say hi, Greg.
Hi, Greg.
I don't have my camera on. I'm kind of looking like Hal from 2000 right here, bumping up and down. It's pretty cool. This is a video. It's just kind of a fun video. We're just going to mess around with Fibonacci sequences. Actually, not too much of the sequences, but the golden ratio and what I call Charlie's angle. Is there another name for that, Greg? Charlie's angle?
Charlie's angle. That's a good answer.
Anyone else?
It sounds too much like the old TV show, doesn't it? But I guess Charlie's angle.
Charlie's Angels. Yeah. We'll get into that. All right. So this is about, well, I don't know if it's the most beautiful argument of the zeta function. I think it is, especially because what it produces. So this is a general argument. Actually, you can enter any number of values in it, and it's always going to give this really special angle that we're going to talk about. And it is very beautiful. I mean, I don't think anyone's going to argue otherwise. You'd have to ask, well, why is it in the Great Pyramid? Why is it on the steeples of so many beautiful churches? So it really is a very important angle, and we're going to get into that. All right, now I have new software, as you're seeing, and I don't really know how to use it, and I put the slides in the wrong order. So let me see what I can do here. Okay, so now we're going to get a paper. Now this is the Riemann hypothesis proof, but it's a longer version. Since Greg's on, we're going to do DuckDuckGo search Greg Volk Riemann hypothesis. And the first one comes up as academia. Are you in academia still? .edu, Greg?
I hardly ever go on there, but I guess technically I have an account there.
All right. I like ResearchGate. So anyway, that's the second one comes up. And let's go back. And then all right, so it's I just while we're there, I'll check that. We got 14,000 reads. That's pretty good. Plus, it's kind of like what it was last month, I think. It's up by a few hundred.
That's slow and steady.
Yeah, but it's definitely went up. I got a couple more recommendations in the past week or two. So, or not but on my side. Okay, and but it's not this one we're going to grab. It's the longer version. So, the longer version has all of the research that brought us to the proof. And it has all this information about the oscillators and all of that. So we're going to use that because without the Riemann oscillator, you can't see the beauty. You really can't. So I've been kind of in my mind thinking of what is the Riemann oscillator, and it is the Riemann zeta function turned on, I guess. So for 100 and some years, it's been waiting to be turned on, and we just did it. And now you can see all this whole other side of the zeta function. It's very beautiful. And here's the thing. Let me ask a question, Greg. You like to do quadratic equations in your head, right?
Oh, I love to do it. That's all I ever do.
Watch it. I love to watch it. It's very. Now imagine somebody. I don't know how many thousands of years ago was it that they discovered the quadratic equation?
Well, that's an interesting question.
2,000, 3,000.
Did the Greeks have a quadratic equation? I
don't know how.
I guess they did. Yeah, they must have. So yeah, I don't know that they explicitly, they didn't have algebra, so they wouldn't have expressed it as algebra, but they had what amounts to the quadratic equation. Yes.
Yeah, they were able to build things off of it. Mm-hmm.
Yes.
Now imagine
they didn't have trigonometry either. Everything was just mapped out. So
they might have a different way of doing it. Yeah.
Yes, but in effect they did. So I wouldn't say they had it the way we think of it in modern terms.
Well, let's say in modern times, let's say 1,500 years ago or so, somebody came along and presented the quadratic equation, a proof of it, 3 guys, and the world said, we refuse to accept this.
Okay.
Think of all that would be lost. Think of all of the discoveries and accomplishments built off of the quadratic equation that you would not see or have, and all of the beautiful structures that are built from it if the world refused to accept the proof of the quadratic equation. In my opinion, that is what is going on with the Riemann hypothesis for the reasons we're going to show here. Because as long as people are not accepting it, they're not digging into it and seeing all the beauty that the oscillator presents.
Right. Yes.
And there's some neat stuff that we're just kind of messing around with the past few days, and there's so much there, particularly in terms of sacred geometry. All right, what's sacred geometry, Greg?
Well, can I say a word about that? Of course, I'd like to, in my opinion, I'm okay with using the term. I know, but honestly, it just means geometry. Yeah. So for whatever reason, the word sacred gets thrown in, and it actually comes from the Jewish Kabbalah or Kabbalah. I don't know how to pronounce
I always
that.
say Kabbalah, but I don't know how it's properly pronounced.
Yeah. And so they attribute, mystical meanings to certain geometric shapes, and they call certain shapes sacred because of that. And somehow among certain circles, the word sacred gets attached to the word geometry. I'm not a fan of that. I just soon call it geometry. But
right.
when they do, I don't bat an eye. It doesn't bother me. But they're actually attaching religious significance to it, which I don't ascribe to.
So that's what I always say is, what's the rest of geometry? Sinful geometry?
Yeah, simple geometry. Yeah, I mean, geometry is geometry. So, and the people that do it, I mentioned George Leoniak, who I have a lot of respect for. I mean, the guy has incredible intuition. He puts together these classes, and he's just putting out new content all the time. And he works with Charlie Zeiss, who we're going to talk about, and he constantly uses the term sacred geometry. And I've asked him what makes it sacred. I don't know. That's just what everybody else says. So, and that's as far as he's gone with it. He doesn't really care. He's just really into geometry, and who am I to say that's bad? So
right, and I think they were using this. There's a term for it, and Charlie talks about it, which we're going to get into. Actually, not going to get into too much, but that the Catholic Church had. It was a teaching they had with their architecture that they stopped. I don't know, 500 years or sometime they stopped doing it. I think it became too occultish within the church, and they stopped doing it. But the problem is they lost a lot of the beauty in the construction of their churches. I mean, there was something very beautiful about the geometry that they were using.
Well, and just to back it up a little further, in the days of Pythagoras, there was kind of a cult almost around the study of geometry, because they maybe it's because they prized this information they were discovering so highly that they just wanted to keep it among themselves, kind of, although it's now common knowledge. I guess it's become profane in the sense that everybody has it, and so what, and what's the big deal? But it is actually very beautiful and very elegant if you study it. And so, why not call it sacred? I don't, I'm not, like, again, I'm a Christian, so I don't ascribe, religious significance to it in any way at all, but it is very beautiful. And that's one thing I'll say in their favor, is that they do appreciate, the beauty of geometry, which I think is great.
Yeah, and Pythagoras, on that, he would make his students fast for 40 days before he ever taught them the concept of zero.
Right.
He said you need to really completely clear your mind and body to really understand that zero or nothing is a thing.
Imagine if you had to fast to be able to go to math class. I wonder if a lot of people would just say, I'll just skip math class.
Well, if they treated it like a religious experience, I could see, they're getting information of the universe, how the universe works. Yeah.
People would really want it. Yeah. I mean,
so that's kind of what we're going to dig into, is this, as all of this and the construction of it in terms of the Riemann oscillator. And you can get all this information, process a value of the Riemann zeta function going through this geometry. It's really kind of neat. It gets deep, but we're going to take one step at a time. All right. So if everyone's got that paper, I don't know if anyone was doing all there, but so who's Charlie Zeiss? We're going to have a podcast, as I mentioned before. Greg and I and John, another guy, started a podcast. We got some really neat guests there, and the one premiering this Monday. If you're watching this as this is premiering, go over to Unpacking the Problem and click the subscribe, click the notification bell, because he's going to go and delve in this topic in a broad but much vaster, how would you say, coverage, I guess. He's just going to go all over the place with it. And I just have a few things I'm going to share that he's going to be presenting. So this is Charlie Zeiss. And what is that structure? He calls it the Russian pyramid, but whenever I do a search on it, it comes up with a billiards ball, game or something. But what is the Russian pyramid?
There's a series. How do I want to say it? We have to, first of all, talk about the number phi. We can't talk about any of this stuff without.
I mean, the structure itself.
Well, it's based. It's the size of it has. If you were to draw a triangle, okay. So imagine a pyramid, and imagine that it has a point at the apex, at the very top, another point at the very bottom, under in the center, and then another point on the side. So we draw a little triangle of those 3 points.
Yeah.
And that triangle has properties that are connected to the number phi. And so one way to think of it is if you imagine the hypotenuse being 1, then one side, the longer side, the height is going to be square root of phi cubed, and the length, the bottom will be square root of 1 over phi cubed, and the side would be 1. That's one way to do it. We could multiply through by square root of phi cubed, and we could get the outside is square root of phi cubed, and the height is phi cubed, and the base is 1, which is normally the way it's looked at.
I got some images of that. Maybe a visual
Oh yeah.
will help.
And now if you want to think of 2
mhm.
triangles kind of side by side, which is the way we think of looking at the, projecting into the pyramid, and that's the way Charlie usually thinks of it. Then that isosceles triangle is going to have, it'll have 2 on the bottom because 1 each way, and it'll have phi cubed on the sides. So that's another way to look at that particular.
And he believes
that's called the Russian pyramid.
So
now, if it's just phi, then it's a Giza pyramid, which is the pyramid we see, obviously, in Giza.
Now, question: this structure, though, he always has as his backdrop and behind him. Is this an actual building, like a mall, or is it somewhere in Russia?
Oh, that's a good question. You'll have to ask him that. I don't know.
Well,
it could be. I wouldn't be surprised if that's maybe a picture of an actual.
I think so. He built it or something,
or maybe some contemporary building. It's beautiful. It looks like it's gold.
Yeah,
I don't know.
All right. Well, let's go here, and Greg, you could go through some of this.
Well, sure. I mean, the golden ratio is what's usually a sequence of numbers, not an addition of numbers. So 1, 2, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5.
I apologize. I was hurrying.
8. You don't add them all together, but that's okay.
No,
and if you take the ratio of each subsequent numbers like you did, so 1 and 1 to 1, 2 to 1, that's 2. 3 to 2 is 1.5 or 1.5. 5.5 to 3 is 1.67 or 1 2/3. 8/5 would be about it'd be 1.6. So in other words, it'd be 1 3/5. And then we get closer and closer. We kind of oscillate around that number. And if you just keep going to infinity, it reaches the number 1.618033 and however many digits you want. And we call that the golden ratio. And that is the number that you see in the spiral that you're showing.
We could do the same thing here too. So if we have 2 blocks that are 1 unit by 1 unit.
Yeah, and as you expand out, it gets more and more. Each of those little arcs forms a quarter of a circle, so it's not actually, a perfect spiral, but it becomes more and more perfect as you get further and further out.
Now, most people that are coming to this page probably know all this stuff and go, "Okay, we heard all."
Yeah, I know.
But there are some areas we're going to get to that a lot of people nobody's ever seen. But then we're going to kind of open this up for everyone. And so as you see that this is prevalent in nature, and I don't mean, common. I mean, it's everywhere in nature. So you got it from, every little fruit, sunflower, snails, the galaxy. I mean,
and I'll just say there is a reason why these things form this special number a lot. And it has to do with the fact that nature just likes to take the previous 2 generations and use it to build the 3rd generation and so on. And so that's why we constantly, without getting any more detail than that, that's why we constantly see that number in nature and in art.
Yeah. Do you think there's something about the path of least resistance in that direction, in that way?
Absolutely. Yeah.
I think so too, which is really interesting when it comes to that angle. We're talking about, air resistance and all this.
Well, that's part of what we want to talk about today is there's structural reasons why these particular angles are preferred. So we're looking at the Giza pyramid, which everybody recognizes. Now, the angle I'm talking about would be the angle from one side. Okay, let me back up. Normally people talk about what's called the pyramid angle, and it's about 51 some degrees, and that would be the angle from the horizontal along the side to the apex. That's 51 degrees.
Just a little over 45
and then if you imagine there's a little isosceles triangle that's formed from the one side and the other side and then the apex. If these are each 51, then what's the top angle? Well, that's the special angle that Charlie talks about. It's 76.6 0.345 degrees. And that's why you call it Charlie's angle. And I guess that's as good a name as anything.
Well, he wrote a book with the angle as the title. So
yeah,
it's like,
yeah.
what else?
So,
there's obviously not any other name to refer it to.
Right. So well, what's interesting is in the Russian pyramid, which is going to be steeper, much steeper. Okay. It's going to have an angle on the side, which is 76.345 degrees. And then the top is, what is it?
27.039,
something like that. So, and normally when Charlie does his measurements, he measures the apex angle, the top angle, which most people, when they look at pyramids, they think of the pyramid angle from the side.
Yeah. If you like,
we just have to get used to that little difference. You have to, you know how to do triangles. We take 180 minus twice that angle. And there you go.
That's right.
Yeah.
That's right.
That's the phi triangle I was talking about. We got 1 and then phi on the hypotenuse and square root of phi. Now, if you imagine square each side, so 1 squared plus square root of phi squared, which is phi. So 1 plus phi equals phi squared. And of course, we know that's true. That's one of the properties of the number phi. That's probably the most basic property.
And I have, as you know, I have a little theory that the reason that this angle is built into so many steeples and everything in nature is largely for structural purposes. And I'll give an example, but let's show some of the beauty of it.
It doesn't fall apart like other angles would. So an angle that's sort of between the Giza angle and the Russian angle wouldn't be as stable as either one of those are separately. And that's just like weird.
And do you think this has something to do with the extreme and mean properties of it that, that was originally talked about?
I'm sorry, I didn't hear the
Well, the phi is also called the extreme and mean ratio, I believe, or something like that.
Sure. I guess so. I'm trying to think in what context it would.
I should put a slide in here, and who it was, Euler or somebody, or Gauss, somebody
extreme,
named that.
Maybe extreme mean in the sense that you get there when you do an infinite number of these Fibonacci things. I don't know. I'm not sure.
You get the average. I don't know. Maybe you get the average. I have to look it up. I should have researched that, but I was hoping you kind of knew about it. Well, anyway, we have some. That's all right. So we have some steeples, and the podcast is just of Charlie going and doing showing how these things.
Charlie can do a better job at explaining his own work than we can.
Yes, so we're just going to skip through it.
He's done an immense amount of research, and he's not a mathematician. He's just noticed that all these steeples throughout all of Europe, and now he's finding other structures, both in nature and in architecture, that have these same angles. And there's a whole family of angles. I mentioned the two most common are the Giza angle and the phi and the Russian angle. Those are the two most common, but there are actually more, because we could imagine instead of one square root of phi, we could have another triangle that has square root of phi to the fifth and phi to the fifth on the two sides. And that also forms you can just keep going. And phi to the seventh and phi to the ninth. Actually, you can also do the even numbers. So you keep getting these triangles, and those are the ones that he keeps finding in all his work, all these special angles. And Jeff and I believe that that's because they're just more structurally sound than other angles would be. And so that's why we're finding them in nature. You see the funnel there and other things.
DNA
everywhere. Acoustics. Yeah. And it's not for coincidence. Phi is sometimes called the number of resonance. And it's because, the input generates an output, which then can become the input and just copy itself. And it does. So that's why we find it in nature so often. There's a resonance going on, and something's feeding back into itself and creating these angles. And so you're showing all these pictures, and that's the same kind of stuff that Charlie did. So Charlie's the only person I know who has a book with the book's name is an angle, 76.345 degrees. And that's pretty cool. I'm not aware of it. Does anybody have a book called 60 degrees or
I don't know.
or 15 degrees? I don't think so.
Yeah, so if he was talking about in the podcast how like the tornado, while they kind of are all over the place, the mature stable angle at the base is 76.345.
It's like they're oscillating around this stable configuration.
It's kind of like self-reinforcing of some sort,
Yeah, and there might be several stable configurations. So if it's it might be the thinner one, and it would oscillate around that thinner angle. But it's eventually going to find one of those angles if it becomes stable. Yeah, I believe that's true.
Yeah. So this is kind of where we're saying it's in aerodynamics too. With bullets, they kind of, I learned this from a little military history, some from military guys, is rifling, which is this, spiral thing that you see these little cuts on the side of the bullet before we get to the angle part. The cuts on the side were something that naturally happened when firing cannons. They found after blowing it, the cannon itself started to form this spiral as it shot it out. And what they ended up started doing, and they found it fired better over time. So they just started carving the spiral form in it.
Yeah. So that just trial and error, they found these angles just through trial and error.
Yeah. And then through trial and error, they found that this angle, the 76.35 angle, happens to make the tip of the bullet fly faster. So yeah, go ahead.
Or get less air resistance. And there's definitely, I think there's a reason for it. And the thing of it is science, for the most part, hasn't even woken up to this. They're not even they're not working on it. They're not experimenting with it. They're not.
Somebody is
not on their radar. Well, yeah, but here comes along Charlie Zeiss, and it's like, okay, he's discovering this new thing.
Well, the Russians are too. The military.
You think people be jumping all over it? Like, I want to know what this is all about. But so far, not so much. I think the day will come. I think there is definitely something to be discovered in all of this. And I wish I had all the answers, and I sure don't. But
no, so
I'm convinced that there's something. Oh, I love this picture, the geometry of the egg.
Me too.
So we're seeing the number phi all over this.
Purposes.
All over this picture. It's not exactly the phi angles, but we're seeing that number. Whenever you see that number, it ought to perk up your attention. That there's something going on. An egg obviously is nature.
And I think this is
why isn't it a sphere, or why isn't it some other shape? It's the most strong shape.
Yeah, the structural integrity of this is that the egg is 1,000 times stronger from the top to the bottom than it is from the side to the side.
Yeah.
So that's because of this. You see, it has this 1 to they have 1 to.
So when you're making an omelet, do you ever crack it on the end?
No. So and I think that's the
crack it on the side.
Yeah, I mean, so if you think you've got a chicken egg, of course you want the heavy side to go down and the strongest side to point up. And for some reason this is much stronger, and so that's why I think that is beautiful. All right, let's see what I don't know. New with this software, I'm not really sure why that is there.
Well, it's a nice J. It's a good letter. I like
Let's see if I can get. Let's see.
I'm not sure where you're going next, but we'll go ahead.
Trying to go to the slide presentation. All right. Let's see.
Anyway, the number phi, we mentioned earlier about sacred geometry, and those who are interested in sacred geometry, they definitely, as a group, believe that the number phi is super special, and they're more interested in it than your typical mathematician, at a university. And that's a shame. There should be a place where they can come together and make some discoveries, because I'm convinced, as you are, that there are discoveries to be made. So
I don't know why mathematicians aren't, and this is kind of the reason. So I found some of these things when working with the Riemann oscillator, the graph. I'm like, I didn't write about them. It's because you're trying to reach out to mathematicians and you want to be respectable, and this doesn't look respectable to them, but it is beautiful and it's all in nature, so it should be something that that is taken seriously. So this is how you get the value of.
That's one way. There's other ways, but
yes, it is. So it's just.
This. Let me just explain now. If you can kind of remember that picture we had before of the pyramid, and it had the phi triangle, has 1 square root of phi and phi on it.
Yeah.
So the sine would be the hypotenuse, or the 1 over the sine, which is 1 over phi. So we want the angle that gives us that 1 over phi would be the I guess that'd be the pyramid angle. That's the 51 degrees. So the sine would be the height. So that'd be 1 over square root of phi. And then we just multiply by 2. That's why it's 360. Okay. Yeah, there we go. And 22 times the difference is that 27 degrees. So
all right, which is the top of the Russian pyramid.
You can also get the pyramid angle, just 180 minus 76 divided by 2. That gives you the 51. So you get that also.
Yeah. All right, so now let's kind of tie it together with the Riemann oscillator. So this is the Riemann oscillator. I have it as A, let's see, in the terms, the A function, the B function, and C function. But because they're derivatives, we can just say the derivatives of C, which we're going to get into. So let me get to that slide, and then you can talk a little bit about the oscillator. But if you think of the terms of the oscillator as a finite state machine, with every finite state machine, you have a regular expression. This would be the regular expression of this. So this is a function, and you then you get all of these in a sequence. So if you integrate the first, you get the second, and if you integrate the second, you get the third, and so on and so forth. So that's such as derivatives work. But let's go here. There's only 3 terms, so you only need to do it 3 times. All right, so if you integrate that, you get 1 over s minus 1, which is in the first term of the Riemann oscillator at t equals 0, which we're going to go over. All right, so let's kind of go over here. But because you can do this, then we get this probably, which is more familiar to you, Greg. Does that look more familiar in terms of
sure, yeah.
Driven? All right, explain what an oscillator is, and then maybe a driven harmonic oscillator.
Just in general, I mean, I'm speaking as an electrical engineer. We see an equation like this. It's second order, and the variable is t. You forgot the dt squared. There should be a d in the numerator.
Yes. Okay. Sorry.
But anyway, a derivative with respect to t squared plus something times a derivative with respect to t, and then plus a constant. That's a second order differential equation. And generally, the response of a second order differential equation, the coefficient of the unitary term, the omega naught, that would be the how often does it go back and forth? How often does it oscillate? And then the nu term, nu sub s, in the which is the part of the variable that goes with
damping ratio,
the dct dt, that is the damping. So that's going to tell you. So we got an oscillating, but it's also getting a little less as time goes on and eventually falls away. So that's telling us how quickly it falls away. That's how mathematicians, and I guess
so most
people look at it. The term on the right, the zeta sub s, that would be the forcing function. That's telling us how, in other words, I'm having somebody push this swing, a little bit.
That's good. There's a good example. I was looking for an analogy. A swing.
Yeah.
All right. So a swing without being pushed would not be a driven harmonic oscillator.
Right. And that's what makes it driven. Correct.
Is there's extra person, an external force that's pushing and keep maintaining it. Okay. Now, a really quick, well, it's not really important, but there's also overdamping, underdamping. What's the other two? Undamped and
undamped would mean nu sub s is 0. In other words, it would just oscillate forever,
which is really relevant to the Riemann hypothesis.
I mean, the real world doesn't work that way. Yeah. And
no, but they have it. They have it in the description. I mean, but
sure. Yeah. I mean, that would be, and then I guess overdamped would be, it's going to eventually die down, and underdamped means it's going to explode. It's going to get bigger and bigger. So those are your 3 possibilities.
All right. And then there's one other. It's kind of, I don't remember what it was. Underdamped, overdamped, undamped, and something else. But it was like a door shutting. Door shut kind of goes and it goes boom, 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 and then it
I'm sorry. I'm forgetting what the 4th possibility might be.
Yeah.
No oscillation at all, maybe, where omega is 0. I don't know.
Underdamped, overdamped. Oh, put it in the comments. All right. So can you explain the omega here really quick? You touched on it, but
okay. So if the forcing function is, there's what we call a natural response. So if you let a spring go, it's going to oscillate back and forth at its natural frequency, and that's determined by the spring constant, we call it, and also the what is the other deal? I guess how far you pull it. No matter how far you pull it, it's going to be it's the natural characteristics of the spring is going to determine the what we call the natural response. Now, if the forcing function, which is omega sub s, is equal to the natural response, you might get, so it's like pushing on a swing. If you just keep pushing, eventually you'll go higher. If you're because you're doing it in sync with the natural response of the swing. of whatever it is that's oscillating, and that's always an interesting case when omega naught, the natural response, is equal to omega s, the forcing response.
Good. Now, Greg, you're being a very good sport. You have not seen this slide.
I have not seen any of this.
You're presenting it, and you haven't even seen it. You're like, respond to each image you see. No, okay, so you're doing it really phenomenal.
Well, you put my name on it. I feel like I know
it's
what I'm
not
talking
fair.
about.
Well, I asked if you do it. All right, so what we're going to do is we're going to turn this oscillator a function of s. So we're going to give s to everything, and so we do give that that frequency. Giving it arguments of s. All right, and let's see what we got here. Okay, now this is what we have proven in the paper, that when t equals 0, this oscillator does reduce to the zeta function. And yes, so there may be typos in this presentation. There are no typos in the paper. We haven't seen it. There have been, but they've all
okay. There's supposed to be a D in the bottom.
I don't have the D in the denominator, but just so you know, we'll try to notice them as we go. So there's typos. Okay, and then upsilon we have defined as this long.
I said new, and it should have been upsilon.
That's okay. New. It looks like just a new, very much almost identical. And then the omega sub s is just simply I, imaginary complex conjugate of s. So I times complex conjugate of s. That will get you everything you need for the oscillator. Oh, it did that thing again.
And I'd just like to make a comment about that in general. The oscillator, if you can think of it this way, it's a way to think of Riemann, the Riemann function, in a graphical way, which is really cool. So you taking these equations and made them into something that we can visualize. I think that's neat.
Yes.
And that's not in the smaller version because it's sort of not necessary, but it is kind of cool.
It is very cool.
And that's also because this stuff that we're talking about with Charlie is very visual. It makes sense to go back and look at the Riemann oscillator just with this specific value. So, all
right. So we're going to bring in something really good, some trigonometry. Not sacred trigonometry, but as Michael Spivak, I don't know how to say his name. Are you familiar with him, Michael?
Yeah, sure.
Okay, am I saying it kind of close?
I think it's Spivak. Yeah.
Okay. The world's sneakiest substitution, undoubtedly, is the tangent half angle substitution. So. Yeah, it's where you're going to set t equal to tangent of x over 2, and x is equal to 2.
Sneaky mathmaticians, then.
Yeah, it is kind of. It's like
it is cool. I agree with you. I just never heard it called that before.
That's what his thing in one of the books he wrote. So yeah, he just kind of said it's sneaky. All right, so this is kind of it is. It's like kind of like, are you sure that's legit? But it is. Then there's a number of proofs for it, and it becomes very useful. So we get these results from the substitution. Sine of x is equal to 2t over 1 plus 2t squared.
I just like to put an aside. We see equations just exactly like this when you start studying relativity. I'll just leave it at that.
Okay.
Like,
and we're going to bring in t to our oscillator, and we're going to construct the oscillator. So we were talking about oscillators, and so if you have, like Greg was talking about a weight bouncing or a spring. So let's say you have a weight bouncing on a spring, you pull it down and it just kind of bounces back and forth. If you were to take a wheel and say you put like a red, I don't know, like a wheel from a bike turned upside down, put a marking on it, had it spinning on the wheel, and you turned that wheel to face yourself straight on, it would appear just like it's going straight up and down, like on a spring. Does that make sense, Greg?
Yeah.
So that shows that real space is identical to phase space in this regard. And so there's often times where
can I just back up and say phase space is just a way of, it's just a mathematician's tool really of analyzing something from the point of what's the frequency going to be. So we can actually remap everything just in terms of frequency instead of in terms of time. It's not that big a deal, but it sounds kind of almost mysterious, almost like sacred geometry.
It is
that haven't seen it before. It's a little weird.
Well, there is a weird thing that I'm going to do that we were doing with the tangent half angle, and we're going to make this orbit time, just like a clock going around. So it's going to have a geometric property that's going to show all this really neat stuff. So we're going to set that to time. So kind of just so you know when we see it, we're going to do it step by step, because as Greg knows and everyone knows, when you see the final graphic, it's a big cluttered mess. So the only way to really study it is to understand how to build it together. All right, so But so we're going to do that. We're going to sub out T for U. So we're going to just no longer call this substitution T. We're going to call it U, and we use T for something else. Just so you know, we're kind of get rid of him. Now we're going to go to R.J. Walker's proof without words. I sent you a proof without words the other day, Greg, and you go, okay, but I don't know what it's proving. It's like, it should be a mic drop. It should be done. I'm done. You know, I didn't hit the nail on the head apparently. But R.J. Walker used to do this. He was editor of a math journal. He would just kind of go put these every now and then for a couple weeks, just proof without words. It'd just be a picture. It's like mic drop, walk away, and it was cool. I liked that a lot. This was one of them as a proof of the tangent half angle substitution. So there's many things to say about it. You can go to Wikipedia. There's an article that includes reference to this. But what we're going to do is we're going to put it on the complex plane. So you see this. Do you see my cursor, Greg?
Yes.
Okay. So this imaginary up the top and off to the right. Greg's kind of over there. Let's see if we can move you, Greg, for a second. Nope.
That's
all right.
Story of my life.
All right. So. All right, so now this length, I didn't label A, E, and all this other stuff on this one, but this length over here is equal to the square root of 1 plus U squared, which was T in the other one, but now we're calling it U. All right, so I'm interested in this length U right here, formerly known as T. And all of the rest we're going to kind of expand upon. So now his proof was on the unit circle. So the radius of this circle would be 1. We're going to change that and generalize it, and you can do some really neat things. All right, I'm going to use this button up here because it seems to be more reliable. It keeps flipping too. All right, and so then we get this. All right, so what we're going to do is we're going to start with the cosine of the angle. So I know we're going to get confused because it's supposed to be, we're talking about phi, the gold ratio, and it's often symbolized as this. In this case, I should put a theta. Anyway, cosine of phi, cosine of an angle equals the substitution. Now, what we're going to do is multiply the reciprocal of minus u, and this is in the paper, the longer form, and multiply by the reciprocal of minus u, minus 1, and then raise the power of s. So we did a couple things in the paper, additional steps in between, but for what we're doing, we're just going to skip to that, and that generalizes this. What we get is something kind of cool. All right, we then turn that angle into the argument of s. So now we have that R.J. Walker's proof in terms of an argument. I'll show how that works. All right, go. All right, so it looks almost the same, right? Except for now we have this point on this line going up here. And so I don't know how many degrees of freedom, I think 3 or 4 in this, but if we were to drag this S and move around, the whole structure would change based on that and resize. I could also grab on this point and pull it around. But that argument, or this angle over here, is always going to be the argument of S. Pretty simple stuff, but it's just the start. All right. Didn't I just see
argument just means angle, just to clarify.
Yes, and you and I, we did a proof, a single statement of the argument. Remember that years ago? Little paper.
I don't remember. You put me on. Okay. I don't know. I mean,
you wrote it. All right. Oh, that's okay. All right.
I don't know.
All right. So as you can see, we have a lot of degrees of freedom. We want to get rid of it. So like I could take S could be way out here. We want to have something to restrict some of the movement so that we can give it an argument S, and everything else falls step by step, as a mathematical consequence. So for example, we can limit the movement by labeling U, giving it a value, and S a value. We can limit it by a couple different things. But if we were to stretch this thing, it can, as it is, we can move it in different things. Do you see how it adjusts? Is that making sense, or I'm not being clear?
Sure,
Greg?
that's clear. Yeah. Clear enough. Yeah, the other diagram is a little nicer looking, I think.
Yeah, I know. Well, it's starting to get, okay. So
I'll just make a couple of comments. If you go back to the diagram.
Sure.
Yeah. Okay. So what you're, okay. So what you're calling, so first of all, I call R is the radius of the circle, which in this case is greater than 1. But, and then it should be clear that P is just, and then arg S over 2. I just call that theta. That's the angle of the bottom of the triangle. If you can point to that.
The bottom of this over here.
That's the half angle is okay. Well, from geometry, we know that an angle taken from the center, and the half is going to be twice the angle taken from the side. So I'm talking about what we'd call point A. Can you point to that? It's not.
My cursor is there. You don't see my cursor, do you?
I guess I don't. Okay. Anyway. Okay. Anyway. Oh, that angle at the lower left corner. Yeah. That angle times R, or excuse me, times the secant of R. That equals P. Do you see that? And then U is just R times the tangent.
Yes.
Of R, or tangent of theta of that angle. R gas over 2. So R.
I'm glad you. Yeah.
So P again. I'll just say it. P again is R times secant of theta. And U is R times tangent of theta, where theta equals R gas over 2.
Good. Now, I'm glad you brought me back to the slide because I forgot to mention.
Yeah, well, you were asking me to thing here. Those are pretty simple.
And this is pretty important here, is that in this initial step, we have to, since now this circle can be any size, we're going to limit one parameter, and that is this. We're going to give this unit length. So from length U, which would be 0, we call this E up here, O to E, we have this line going parallel to the real line. It's 1 unit length. Now, the line going up can be any size, but this always has to be 1. And then it allows us to do some really neat, that's simple things. So we still have the unit rectangle in there that allows for certain geometric relationships. All right. Now, there's another thing we did, and this was with the intention of the paper or the proof, but also it allows us to map the Riemann zeta function on here, or to put to graph the Riemann zeta function's values. And really, this was really one of the consequences that results in the proof. So you get this condition in doing this step that this, let's see what is the best way. The absolute, I don't read it all. All this at the top. The absolute value of the cotangent of half argument minus tangent of half the argument is equal to the inverse or the reciprocal of the imaginary part. This only happens when the real part of S equals 1/2. And the reason is because the cotangent of 1/2 the argument minus tangent of 1/2 the argument minus 1 over the imaginary part equals this condition here. And look at the numerator. That numerator, complex conjugate of plus S minus 1, only equals 0 when the real part of S equals 1 or 1/2. And that's really critical in the final proof. But you do not need to, in order to explore what we're going to show here, you don't need to rely on the proof of the Riemann hypothesis.
And I just like to emphasize again that what you're doing is you're taking all we can, I think, in our day and age, we tend to just use algebra so much that we don't think geometrically. But what's nice about what we're about to do and what you have already done is you're taking these, complicated looking expressions and mapping them out onto something that we can see, something geometric. And I think that's really cool. It's not essential. It doesn't make the argument, but it does make the argument clearer.
It's good for research too. If you're trying to find something, that was for me. I'm a visual guy, and I like.
Yeah, you spend a lot of time playing around with it.
So. Oh, a lot, and a lot of things went nowhere. But some of it, there's
kind
still
of like the other day.
Yeah, well, that would have been cool, but it was still kind of. I was doing this already, but I thought I found something really neat.
Do you want to? You want me?
Well, when should we give it to? I got a slide that's kind of similar.
Okay, cool. All right.
I don't mind admitting my hopes.
Yeah, a lot of rabbit holes.
Yeah, but the thing about all of the cool things that haven't been found yet with the oscillator too. So there's a lot here.
I mean, part of the whole, I think a really good mathematician isn't necessarily the one who can calculate the best. And the really best mathematicians are the ones that have an inventive mind that can are willing to explore and kind of look into places that maybe somebody else hasn't looked before. And there's an artistic side to it.
Yeah,
and not every mathematician has that. That's all I'm saying.
Yeah. So we talk about that condition of that only happens when a real part is equal to S. Here are some of the geometric consequences of that. So you get this on the left-hand side, we were talking about the cotangent, all that. So these lengths kind of line up in that way. There's a lot of other things too. I'm going to go to the next slide. I think I have another one. Let me see.
Yeah.
A lot of things line up with this. For one, if we let the imaginary part equal 1 and the real part 1/2, we get phi. That's our golden ratio, which we're going to start exploring. And I've never really understood this, I think, until just this past 24 to 48 hours, why this even happens. And we'll get into it. It was something, the cotangent thing I was showing you the other day, or this morning or last night. I don't remember when it was.
Once you start messing with phi, I'm telling you, it just keeps showing up everywhere. It's like all or none with phi. That's why the number is so unique and special. It just keeps showing up.
Yeah. All right, so there's a lot of things that happen with this graph when you only have a real part 1/2. Okay, so I kind of keep showing. Okay, well, whatever. So what we've done is we have put this PowerPoint into Restream, and it's kind of repeating slides, doing something weird. All right, so you remember that line, that unit length, the unit rectangle over here, Greg, right?
Yeah.
So now we're going to take a circle and make it tangent. This was, I think, the missing link when we were talking the other day. So that outer circle has to be tangent to that line and centered on the origin.
No, I understand that.
And then this is
I didn't before, but now I do. It was in your diagram, and I just didn't see it. So
that's okay. Well, it's hard to see that it's tangent. I mean, you can't really tell.
No, it was. I don't know. I just wasn't. It seemed irrelevant, and obviously it wasn't there because it was relevant. I get it.
Important.
So it takes this line over here a while for me to figure out what you're doing.
Yeah, this line here is not tangent, so we can get closer or farther away this circle. This is the really bizarre and most interesting thing of this. Is the heart of this whole graphic and the oscillator. Is there's now you have, the best way to say this is the planar, what do you call it? Planar section of a double-sided cone, circumscribed internally tangent to that circle, and then another circle internally tangent to that line. And what you get is something very important. The zeta function is all buried in there, at least one part of it. And we also, you have to set, this is one of the what do you call it? Where we're limiting, we're defining this outer circle here as 1 over the imaginary part of S. So now we have S here, imaginary part of S, and this is constraint, and everything else follows suit. So like we can determine U from everything now. We can,
as I said before, in order to do, you have 2 variables, and once you have any 2 variables, then you can figure out everything else. Yeah, they could be the height, the angle, or they could be like the 2 S coordinates, the real and imaginary part, or whatever parts you want to pick, and everything else falls into place once you have those 2.
Yeah. Now remember the first term of the Riemann oscillator. I labeled it A sub S of T for a reason, because we want to focus on it. It's a lot easier than calling it the derivative of C. It is the most important at this point. So the at T equals 0, the value is at that point geometrically. So the A sub S of 0 in the lower left, since you don't see many, you follow that up to that point there on the inner circle. That is that value 1 over S minus 1. And that is the first term of almost every representation of the Riemann zeta function. So the Abel-Plana form, many of the integrals. In fact, it is that term is why the zeta function is undefined at S equals 1. It is because of that term. So it's a very important part of the zeta function.
I would say that differently. I would say if one were true, the other would be also true. So there are 2 different ways of saying the same thing.
Well,
I just mean this doesn't cause it. You can't say this is the cause of that. They're inextricably linked. One means the other. I would agree with that, but I wouldn't say one causes the other. That's
if you're defining the zeta function, an integral, and it has a term that is not part of the integral, and that term is 1 over S minus 1. The integral will not be undefined at S equal 1.
Okay.
It's just that first 1 over S minus 1.
It's semantics.
Okay.
I'm not talking about anything that's all that important.
No, it's not. All right. So now if we take that function, which is at the top, I do. If you take this function, the functional equation of it at the top, and all other t's, I don't know, 3.14 t equals whatever, t equals 1.2, you get this spiral here that goes on in as you would expect. That's that function. But the most important thing is that value at t equals 0 in terms of the zeta function. Now, an oscillator, it's all moving parts. But I just want to show where that lies. And we're going to go then to this. Oh, t. Where's t on this? So if you take that spiral, let me go back to this, see if I can get
t is as I understand, you usually t is a parameter that describes this. You're not showing this this spiral that you generate.
Well, that spiral is dependent on t, but so is this a sub s of t.
Well, yeah, anything depending on t is going to change with
so
t.
The t are the circular segments of this circle. And how can you prove that? Is if you go ahead and see this line from a sub s of 0, right? That curved line, that part of the spiral, where it meets up the imaginary part. What is the t it takes to get from there to there?
And it's phi. It's related to phi. Go ahead, finish your sentence.
The amount of t that it takes for this function to get from this point, the origin, to the imaginary line is equal to, you can do this calculation by setting, because remember the real part, the imaginary part was 0, set the thing. You can calculate t, and get this, it is that arc length. Only when the real part equals 1/2, though. But that gives you a signal that it's kind of like it's all related. So you think of this clock. Now, what is the t it takes for the complex conjugate of s? It would be the remainder of the circle. So that's really kind of interesting, I think. All right, so that we got this. It's like a clock of t going around and around, and so I
just want to confirm at this point we're not talking about anything to do with phi. We're just talking about the Riemann oscillator in general.
That is correct. That is correct. So just trying to give. We're going to get to phi.
And I just want to go back one, if you don't mind.
I don't mind.
Just want to clarify. I know that we probably lost the non-mathematician. No, go back to the diagram.
Yeah. Okay.
Where you have a sub t sub 0. That means t equals 0. Just want to be clear in case anybody missed that detail. So in other words, it's like the starting point of that curve that's going in.
Yeah.
And t is the parameter that describes all the points, but when t is 0, it's at that point in particular.
Yes, very good.
Just to be clear.
And also the zeta function at t equals 0 is equal to the Riemann. The oscillator is equal to the Riemann zeta function at t equals 0 too. So
right.
It's a very important point.
T equals 0 is the point we care about most.
Yeah.
Well, why don't you tell us, Jeff, what does t, in terms of the paper, in terms of the Riemann oscillator, what does t represent, and why, if we're only interested in the t equals 0, why do we care about the other values?
Well, you'll for this video particularly, it's because of all the cool things you see in place of it.
Okay.
So you can
but in general, does it even matter? Or does
it is the way, yes, it is.
It's like a limiting thing. Is that what
t? All right.
I just want to hear your response to that.
Yeah. So there's a number of things. All right. So if you think of it as a machine, then you got to construct the machine, and it's a machine dependent on t. So the Riemann zeta function is only one part. There may be zeros and other analogs to the Riemann hypothesis with the whole oscillator in form. So it's just basically it's expanding on the Riemann zeta function. So the t we are going to use in just a second. I'll show you.
Can I say one more thing?
Please.
I said this earlier. I said that, remember that when the frequency of how fast it oscillates depends on two things, and then I only named one. I named the spring constant. The other one is the mass. So the spring
constant. There you go. That's right.
The mass. Right. So the greater the mass, the slower it oscillates, and the greater the spring constant, the faster it oscillates.
That's right.
Anyway, it's k over m, but whatever. It's been years and I forgot.
So we want to bring up the phase space. Now we're going to show you where t comes in. So there's t is on these arc lengths around there. So like a clock going around. And so where's the zeta function in this? So if you recall what we were doing earlier with u and the tangent half angle substitution, and then also we raise the power of s. All right, so we do a simple little multiplication just to rearrange the structure here of u minus 1 to where is it? I wish I could move your image over. We're going to change it over to u minus 1, which just stays the same, but 1 minus u squared. And to do that, we just multiply it by all this. That is equal to something very... What's that?
You said
so, all right, so look at the
u squared in the denominator.
I wish you could see my cursor. That's one thing with problem with Zoom. All right, look to the top equation, the right side of the equality.
Okay.
Okay, so this is what result we have. And so if you remember, if we get rid of the s, then this would be something from the tangent half angle substitution. Remember, u used to be t.
I did.
We gotta go at the beginning again.
I'm kidding. I'm kidding.
No, we probably lost other people too. Do you remember the original? The original R.J. Walker's proof that had this rational function square root on the left hand side. All right, we're going back.
So you got a different variable now. What used to be t
is
now u.
We're subbing out t for you. A long time.
Yeah, I used to be t, but not anymore.
Okay, hold on. Okay. No, because we're using t now for the oscillator.
You know what, Jeff? I want to take all this stuff and redo it so that it so that we can teach this stuff to non-mathematicians. I really think that's possible.
I know. All right, remember this.
But people that like sacred geometry, not total non-mathematicians, but people that like geometry and stuff like that, but are not really into much beyond that, because that's when we lose them. But anyway, go ahead.
All right, look. Remember this slide?
Yes.
Okay, so with tangent half angle uses the value t. We're not using the value t anymore. We're using u.
Yeah. Okay.
So
I got it.
R.J. Walker symbolizes this u here with t.
He called it.
We're using t for the oscillator for something else.
I think we can handle that.
All right, I thought so. Okay, so we're gonna go back to this. I didn't think it was that complicated.
No,
it's confusing.
Was I complaining? I don't remember complaining.
No, but it is. Whenever you have these variables, I wish we had like 52.
Well, as long as you have a diagram, and now what we're talking about refers to this diagram, then we're all in the same page.
This t is still t.
Yeah.
It's just the other t is now called u. See u off to the left?
Yep.
It used to be called t, but it's not t anymore. It's u. We got to call t this because the oscillator is more important. We're talking about that.
Yep.
All right. So now, do you remember that identity, cosine of the angle, all that?
Yeah.
Okay. All right. We raise the power of s. Okay. What does this equal, and what does it look like on the right? Anything familiar?
Well, I mean, it looks like the substitution you were talking about. No? That not where you're going?
What looks 1 over u to the power of s? What does that look like?
Oh, I mean, that's starting to look like a factor in a term in the Riemann oscillator.
The zeta function, 1 over n to the power of s. 1 over here. Now, if we change the infinite series of the zeta function is 1 over n to the power of s, right?
And can I just point out before you go on? I'm sorry. When you raise something to a complex number like that, that is a spiral.
Yeah,
just whatever that's worth. That's what a spiral looks like mathematically. So just for those that are visual only, that's what that is.
All right. So what we're doing is we're moving this closer to the zeta function. The zeta function is in here. At least the function of it. Let's move to the next slide.
I'm looking at those terms in the next line. Yeah. Okay.
Should I go back?
Okay. Yeah, I was looking at something else. You got a lot on that page, and I was trying to figure it all out.
Let me go back. All right, let me go back.
Okay, the sequence here, you got 1 to the 5th to the s, 1/5 to the s. Why do you have the same term twice in a row?
Because that's what arises.
Okay, for
2 and 3, they have the same value.
Wait a minute, isn't u going like u equal 1, u equal 2, u equal 3? So when u
0,
equals
1,
I should have 2 in the denominator. When u equals 2, I should have 5 in the denominator. When u equals 3, I should have 10. I'm missing something. And then 17. So I don't know. I'm not tracking. I'm missing that. I don't understand how you're generating that sequence, but go ahead.
Well, I got all the values confirmed.
Is u meant to be integer values, 1, 2, 3, 4, or start 0, 1, 2, 3, 4? Okay.
Well, natural numbers in this case, yeah.
Yeah,
0,
I get it,
1.
but okay, something's not right, but I won't belabor it.
Well, wait a minute. Let's go and let's see if I can pull it up. All right, I'm going to pull up. Do you see my screen here?
Are you maybe doing negatives and positives?
I'm at Wolf. Let me go back.
I don't know how you got 13. How'd you get 13? I get how you got 17 and 37 because that's
All right, hold on,
36
slow down.
plus
Stick
1
with
and
one.
15.
Stick with one. Stick with one. I don't know where you are.
Sorry. I'm just trying to figure it out. It doesn't make sense to me.
Here. All right. Here's what I'm gonna do. I'm going to Wolfram Alpha.
Oh, I bet you are maybe reducing it, something like that.
All right. Give me the function because I don't have it on my screen. I'm calculating it really quick.
Okay, so 2/13 should actually read 4/26. Then it makes sense because my u squared is going to go 1, 4, 9, 16, and 1/5 is also 2/10. If you actually wrote it as 2/10 instead of 1/5 the second term, and 2/13 should be written as 4/26, then the pattern is there. It just was, you're reducing the fractions. Now I get it. Did I go too fast?
No, as long as you're on the same page.
I'm on the same page. It took me a minute to figure that out.
No, that's okay. That's okay. All right. Let's go forward now. So we see this u minus 1 and all this at the bottom, right? This is now, this you can get the zeta function out of. And here's how. So you just take the sum of those, of each value of natural arguments u. All right, good.
Yep.
And then you ended up with the Dirichlet.
Is there a name for eta sub s? Sorry, is there a name for eta sub s? Is that the eta sub s? Isn't that somebody else's function? The alternating zeta function. Thank you. Okay.
Alternating zeta function,
years, I forgot.
which you can get the Riemann zeta function from by just simply dividing.
Once you got one, you got the other. Yep.
Good. Got it. So these are important, and these are on the graph. Where are they? Right here. So if you take this line, our unit length, which is super important, remember the unit rectangle off to the left, and we come down, there's an angle. The initial angle always equals -1, just as the alternating zeta function always does. And now we have t instead of u, but we can let t be natural numbers, right? So we want to consider t can be anything, 1.315, whatever. But if we only take the natural arguments of t and we take them and sum them up, we have the minus alternating zeta function values. Okay. Now, what is super cool, where phi comes in, is unfortunately covered up right there with the screen. Let's see if I can. How is it?
The best stuff, but I'm
it's
not
right
going
there
to show
in the lower right. You see it right behind where you are.
Well, hold on, I didn't put me there.
I don't know how to move it around. I wish you were mobile. And then the top. All right, so we can see at the top. If you take the cotangent. Is
Jeffrey working on it?
Nah, he's upstairs doing something. No. All right, so
you can't move it, huh?
Here, if we take the cotangent of this in the lower right-hand corner, with when the imaginary part is a certain relationship of real part of s divided by 2, and t equals 1, the initial 1, you end up with the golden ratio. So that's then connected to the values of the zeta function and all of our geometry. So what that inspired me to do, well, one, it gives this really weird identity, which I don't know if I have it in the next slide, which is this. I just want to
point out to non-mathematicians, this is the sort of thing that gets mathematicians excited.
Like, why honestly, is that?
Like when something unusual happens. But yeah, I'm not surprised at all that we see the number phi. Once you introduce it, it shows up everywhere.
So why is phi there though equal to cotangent? This cotangent. You were looking at it earlier.
I haven't. You gave me this yesterday, so I haven't.
I know it's kind of like, why is that there? I put it into Wolfram Alpha, and it says yes, that equals square root of 5 plus 1 divided by 2. But I'm like,
I will figure it out. I just haven't.
That's really weird. All right, but that's cool. And so then I get this idea. Well, I'm gonna show some other things before I get the idea. Is how beautiful can we make this? Oh, here it is. This here is now printed out. It's this new form of the. Actually, I put a plus sign here. You can do minus, which brings the 1 out here.
Putting a 1/4 factor in there.
It's the well, that's already kind of there.
Okay.
It's all right. You see that 1/4 out front?
I do see that.
So let's talk about the angle, because it's obviously pretty important. So you have these points for all t, an infinitesimal t, or any t, not just the natural arguments. You're going to get this this radius to the point, which is equal to t to the power of minus the real part of s. So that's going to be how far out and away from the origin it is. And then you take a 90-degree turn left from that, and then you have this another angle that's tangent to the spiral as it comes. That is the angle right there. It gives, well, the angle off that point, it gives all these really interesting properties. But that angle, that point itself, are the points within the zeta function, not summed, but the actual, the different terms of the zeta function. All right, so of the infinite series. So here's just kind of a new definition of phi.
Wow.
I don't know if it's a new definition. It's just you're going to figure out why it's that way. But
the old definition is probably simpler, but this is good.
It is. Well, but it's kind of this is the reason why it shows up all over our graph. Not only one argument. So what is the most beautiful argument? It is the one I went and found that brings everything onto the graph, even including Charlie's number, your
Charlie's
27.
angle.
So everything comes out just from this beautiful argument. Let's kind of, you want to go through and point out all the different things. You got the conjugate of phi up there.
Sure. Yeah. I mean, I can just go through the process I went through to figure this out.
Okay.
So you actually, well, okay. So what I call theta is 76.345 over 2. That's the angle all going all the way back to point A, we used to call it. And then the larger angle is 76.3. That's the argument. That's that trigger. So we're seeing several instances of both the Giza triangle and the Russian triangles. So now, remember when I was talking about those triangles earlier? We can talk about the full Giza. The full Giza is the isosceles triangle, whereas the half Giza, generally the one we use is a right triangle with the center at the bottom. And the same thing with the Russian. We have a full Russian and a half Russian, like a half Nelson. Okay, so I wish
the parent was Lithuanian.
I wish you had some points here, but there are several Giza triangles. So or what I would call half Giza triangle. I'm just going to call them Giza. So I wish you could label these points. Point C is the point on the circle that's where that lies along. There's a line that goes through your point S and then hits the circle. That we'll call that point C. That triangle there, that from the origin and then straight down, that is a Russian triangle or a half Russian triangle. And then there's several Giza triangles, and that would be from that same point to the same point below, all the way over to the side. That's a half Giza or a Giza triangle. There's another half Giza going from the origin up to your point, as you call it, U or T, which is phi above it, and then over there, that's another half Giza. And then we got another half Giza with the line that goes 1 on the it's above the circle, and then above that little right triangle is also a half Giza. So if you were to finish that, they would all form Giza pyramids if you took and mirrored them. So and then I guess there's technically another one. If you were to take the one down below and map that, you see that little dotted line below the number 1.
Yeah.
That's another Giza triangle right there. So there's several of them in that diagram. And then I guess you could draw another one from that point over to all the way over to the side and up to your point C there. So there's a whole, every one of those has those same proportions, and the proportions are 1 phi square root of phi.
Now, why is this 2 naturally a consequence of this, coming out?
Yeah. So for example, we know I calculated that the radius. What is the radius? Was the radius of the circle
square root of 2 plus square root of 5?
No, not that. The radius is square root of phi cubed. That's the radius. So square root of phi cubed, which would be 3 halves, and then the what you call the height to that point is phi. So we have phi to the 3 halves, phi on the side, and then phi squared, which is also phi plus 1 along the hypotenuse. You see where it's identified as phi. You can do that all in your head. You don't see what I'm saying? You see phi and phi plus 1. So the radius, I know immediately that the radius has got to be phi to the 3 halves or square root of phi cubed. So I can figure all this stuff out just looking at the diagram. It's maybe not immediately obvious, but like, for example, if I know that the base is 1, then I know the height above that is going to be 1 over square root of phi, and that the hypotenuse is going to be square root of phi. So I have 1 over, so the whole thing is phi minus square root of phi. So that height of that circle has got to be phi minus 1 over square root of phi. And then I just get I know that that's 1 over the imaginary part of S. So I just take the reciprocal of that and I get S. That's how I did it. So, and that turns out to be phi plus 1 over square root of phi divided by 2. And that just happens to be the reciprocal. So a little bit of algebra to figure that out. But that's basically the process. I went to calculate that number 1.202.
Which is
here. 1 plus square root of phi. Yeah, and you thought.
All right, so we thought, yeah, this I don't know how it's in here. I have edited. Oh, maybe I didn't save the new changes. Okay,
that's the old one. You thought that it was actually connected to the zeta sub 3, but it's not. It's like different in the fifth.
Close, like the fifth decimal.
Very close.
Right. So I don't have the
I sent it to you in an email, the two numbers, and they're
Jeffrey sent it to me before. That's why this is all messed up.
It doesn't shock me because I wouldn't expect to see zeta sub 3 there. It'd be cool if it was, but I wouldn't expect it to be something that we could just name and, it would be called a constructible number, and I don't think that it is.
Okay, well, so all right, so what happens is Jeffrey imported this before I saved it, so it doesn't have the changes. All right, but you have determined what the imaginary part is.
Yeah.
I have to. All right, darn it! I needed that last image. The whole point.
I'm sorry.
No, you didn't do anything wrong. Let me just pull it up. You'll write it down. All right, or maybe I can find a different way to share the screen. I'm gonna pull up.
But sometimes we know S and we have to figure out the other stuff, and sometimes we know the other stuff. In this case, the angle, and we have to figure out S, and that's how it worked this time around. So it's a few steps to get there, but it's all, you can figure it out. It's not that complicated. It's just being able to, if you have a mastery of that triangle, the 1 phi square root of phi triangle, you can almost do it in your head.
All right, let me show the general form. Man, all right. So you have found that the imaginary part is equal to 1/2 times phi plus 1 over the square root of phi. That gives 1.
Yeah, the 1/2 is times the whole thing.
All right, good. Now I'm going to copy something and see if I can share the screen to show the general form. Give me a few seconds here because some formatting issues. And then I'm going to see if I can.
There are some neat little identities that you can get out of that. Like, for example, the fact that I don't know if you can do this in your head, but phi plus or minus 1 over square root of phi. If you multiply those two terms by each other, you get phi squared minus 1 over phi. Well, phi squared is phi plus 1. 1 over phi is phi minus 1. So phi plus 1 minus phi minus 1 equals 2. So that's where the half comes in. So you can do it in your head almost, maybe I hope that wasn't too fast, but
that's okay.
But they are obviously reciprocals of each other, and they have kind of a neat little symmetry, which I think is cool.
All right. So this is the general form. So this is the general form of that. Now, if we take that imaginary part, which you said, and we can replace it with any number, no matter what number we put it in here, it will have the argument as Charlie's number.
Charlie's angle.
Charlie's angle, sorry.
We got to get that right.
Let me just type in.
We're going to make him famous. His angle will be going to be more famous than he is, maybe.
Well, there's
can you imagine like 50 years from now, and then you take Charlie's angle and you do this?
See, there it is.
I have no idea who Charlie is, but it just has a good ring to it.
Who's Charlie? I don't know. It's a good name.
I don't know, but that's what it is.
See that angle there, Greg? Do you see my screen?
I see it. I see your cursor now. I didn't see it before, but now I do.
It's this slideshow. It's not showing it. All right, so this is in radians, and in radians that's 76, or in degrees that's 76.
Yeah.
So so this is the where is it? Go back. One more. Right here. This is the identity that is most interesting for me. Let me see if I can go to give me a second. I'm going to copy your A. Coming back. All right. So you have A as this. You know, there's a symbol, phi, which actually takes it. All right, I'll just do this really quick.
Yeah, I hardly ever write it out. If ever I'm dealing with phi, I always use spreadsheets. It's just, I don't have to be typing out all these complicated formulas.
I get you.
I don't do it that way. I do it in steps. I get phi, and then I just use the number 5 forever.
Yeah, but I like
with this, you have to Mickey Mouse and put the whole thing.
I know. Square root 5 plus 1.
It's not elegant.
Divided by 2. I know. I know. You like it that way. All right, here we go. And then square root. All right, there's everything. Now we're going to take all that and replace it for A. We'll see if I made a typo. And it should give our value to a high decimal precision. Yes, there it is, 0.292.
Oh, that's your real part.
That's everything. The real part.
That's the real part of S. Just go back to the diagram so we know what we're talking about. So yeah, I'll give you the formula for that. I don't have it off the top of my head, but go back to the diagram if you would.
Okay.
Is that hard?
Nope. Wait. Where's the slideshow?
Again, we know the angle. Whoa.
Hold on. We're new with this software. I have no idea where my PowerPoint went.
Oh no. Well, that's all right. Bottom. Let me just say this: we know the angle, so we know that S lies along this line. Okay. And if we can fix the imaginary part, then we can calculate the real part. And if we know the real part, we can calculate the imaginary. So in this case, we figured out the imaginary by getting the inverse of the imaginary, and then we were able to calculate the real part. And that's all that Jeff just did. And it's 0.292 something. So I can figure that number out. I don't have it in front of me, but in terms of phi, exactly.
All right, here I got it. This is the actual unsaved one. Do you see that?
Why? Yeah. Okay.
Okay.
That's the correct formula. Yeah.
Yes.
That's the imaginary part, what you're calling A. So the real part is just. I'll give you a simpler. What you just did in Wolfram works, but there's a more elegant way to do it. I guarantee it.
Okay. Well, then we got to deal with it. Yeah, we would have to work with it. All right. Well, that is what I think is. Well, anyway, so you could get, and again, you get the zeta function out of that just simply by taking the points, the natural arguments here along this all the way as you increase t. So 0, 1, 2, 3, 4, 5. Sum them all up, and it will reduce to the value.
In fact, I've got the answer. All you have to do is take that number and divide. But remember, the Russian pyramid is a square root of phi cubed. So just divide that by square root of phi cubed. So you're going to have 1 over phi plus 1 over phi squared times a half, the whole thing. That's the answer.
Yeah, I meant for but I was speaking for the value of the zeta function. Well, that's just a
little simpler. 1/2 times 1 over
We're talking about two different functions, though.
1 over square root of phi plus 1 over phi squared. That is and then you can simplify that even further, probably. So I can't do it in my head, but I can do it.
That's all right.
Anyway, that's gonna also give you a 0.292, whatever.
Nice. Yeah, but it's really and who knows what other arguments there are in here. But you know what the thing is that there's so much to explore with this oscillator, and there's so much to explore in this area. And
well, okay. So if you don't mind, restate for me. I know you kind of already have, but restate for me again. What makes we know what the oscillator is supposed to do. It's supposed to give us a graphical representation of the Riemann zeta function.
Yeah, that's one thing.
And other things. But why? What makes this particular value so special?
This argument here?
Yeah.
Oh, because it pops out all the angles of sacred geometry.
Okay.
all on one screen. Right.
Okay.
That's all. Everything on here is tied right to it. Okay. So it
just keeps showing up. Yeah.
It's just it's every single component of this diagram has Charlie's angle all over it. That's the only reason. It's just beautiful. It's for the sake of being beautiful.
Okay.
And if it's not beautiful, then
it's got to prove something. We don't know what yet.
No, it doesn't need to prove anything.
That's how mathematicians think.
Well, this one is not for mathematicians. This one's for Charlie.
Yeah,
and Charlie's not a particular mathematician. He is a he is enthusiastic about this number.
And that is putting it mildly. Yes.
Yes. So this is the a video for him to promote him and anyone who is fascinated by the golden ratio for the sake of being the golden ratio. That's what this is for.
Or Charlie's angle. And also, we're going to promote it. I'm going to call it Charlie's angle from now on.
That's what I've been doing.
I like it. But there's also the Giza angle and Charlie's angle. Those two, I think, are pretty. Everybody pretty much knows what the Giza angle is.
Yes. So, but if you call it the Giza angle, everyone knows that?
I think so. I think if I said Giza angle, most people that study pyramids would know I mean 51 in some degrees.
Okay.
But Charlie's angle is not as well known. So, in fact, I don't think anybody calls it that. Just
I honestly never knew about it. Honestly never knew about this angle before I met Charlie for the podcast.
Interesting. Interesting. Yeah. Well, so we got to promote it because it's a big deal, I think.
I think so. And also, this also gives a little bit of opportunity to explain some of the Riemann oscillator, and who knows what is yet to be uncovered. Through it, it gave us what we wanted to know to prove the hypothesis. And the cool thing about this is that to use it to find anything beneficial, they'd have to reference our paper. Yeah. Unless they want to steal, but why can't you steal?
Yeah, go ahead.
Because there's 14,000.
Stealing is promoting, as far as I'm concerned.
I agree. Do it.
Well, go ahead. Steal our paper.
Yeah. So, but definitely,
it's like Abby Hoffman said, steal this book. But anyway.
And stealing is the best form of flattery too, in some ways.
Yeah.
Is no. So, to me, I think that is the most beautiful. Now, I think the argument 2 is pretty beautiful for the zeta function. It brought about the basal problem, but I think this one's neat because, I think those angles in phi are the most beautiful angles in numbers in nature, and therefore I think this is the most beautiful argument of the zeta function because, that's everything you get.
I won't disagree with you.
You can disagree. So beauty's in the eye of the beholder.
Absolutely. What's cool about that angle is it's connected with the phi cubed and the phi both, and nothing else. And that's why you see both the Russian triangle and the Giza triangle all over this diagram you drew.
Yeah,
so that's pretty cool. I do have a couple things. Are we close to done?
Please, yeah.
I just you mentioned that I could share my screen, but I'm not sure exactly how to do it. I have a couple things ready to go, but I don't know how to share the screen on this new software.
Look at the experiment.
I don't see it. I'm looking. I see.
All right.
If we can't do it, it's not the end of the world. But I just got a couple, like that one that sort of it's expanding. It's a bunch of Giza pyramids, and they're expanding outward and just keep going on forever. I think it's kind of cool.
Try it. Press H. Press H and see if it shares.
Press H, the letter H on my keyboard.
Yeah.
Oh, how about that? Okay. Chrome tab. So, all right.
And then just click on it, and it should do it.
Okay, let me try that. Do you see it?
Yeah. Hold on. It's just show on stream. It's showing. There it is.
Okay. So all this is just that's a Giza pyramid. These circles are geometrically spaced. It's a geometric sequence, meaning that each circle, the radius of that circle is exactly phi 1.618 times the one below it. And so they're just expanding out. And that if you were to draw from that center point out at that particular angle, then you get Giza pyramids everywhere. So that's kind of a cool little way to show that.
I feel like I'm going through a Kubrick tunnel.
Yeah. I have another one. It's just also quick. I can explain. Sure. It's just kind of fun visualization. I could do the same with the Russian pyramid and everything else. If I could find my mouse, here we go. Okay. I've got another one to show. Looks like I have to I press H and no, don't want to do it here. Hang on. Go here and press H. Okay. It's not working now. I'm not sure why I'm not getting it now. I was before.
All right, maybe I have to tell.
Well, not a big deal. Maybe I can't seem to it's not a big deal. The other one is just basically showing a way to construct the Giza pyramids and the Russian pyramids and that whole. Remember, I said there was a family of pyramids, a family of triangles.
Yeah.
And this shows you a way to construct all of them with one diagram, which is kind of cool. But I can't seem to do it. I don't know what I did. Why Maybe do I have to get out of this? Okay, now let me try H.
Yeah.
Let me see if that works. No,
I'm
still not getting it. Okay.
Now press H again.
Okay.
I just overrode you. So
maybe I have to stop sharing and then start again. Sorry. Let me try it now.
Yeah, you definitely have to hit stop.
Okay, I have to stop sharing and then start sharing. Okay, now I got it.
Yeah, that's
okay. Let me try that one. This looks like the right. No, that's the other one I did already. Okay, here we go. This one right here.
Okay. Now give me a second to share.
Hopefully you can see it.
Yeah.
All right. So can you zoom in a little bit?
Yeah.
Zoom in at least. Yeah, even more. We don't have to show the bottom circles. You get the idea.
You can zoom in on your end. I can't zoom in on my end.
I can't zoom this particular one that I can see, but that's okay. All right. So what I want you to notice again is the same family of circles. Each circle is exactly phi greater than the one below it. And we have that. Then I drew a circle from the apex, the top, through the center. And when I did that, I get that. Remember those yellow angles I got in that other one? That's the same angle. That's how I got it. Okay. And then the top red triangle with the blue base and the top, that's a Giza pyramid. And then the second one is one of the even numbers. The third is the Russian pyramids. You see where it says 76.345 degrees down there?
Yes.
That's that what we call the sidereal angle there. But there's a whole family of them. There's another one below it and another one below that. There's an infinite number. But the two that we seem to find the most are the first and third, which is both. The first one has the Giza, the 76 up at the top. It's the apex angle, whereas on the Russian triangle, it's the sidereal angle. But those two angles are the same. And I have a couple more that show some neat things you can do with the fact that they're related. And I couldn't seem to find it, but I have another kind of a neat little graphic that shows if you take a Giza pyramid and you draw a Russian one upside down in it, you get Giza pyramids left over with the Russian, and then you can put a Giza pyramid inside the Russian one and get three more Russian ones, and then you can just keep doing that forever. And I have one that did that, and I can't seem to find it. So I'm sorry, but it's kind of a neat little, just a fun little toy, I guess, showing the relationship of those two. And it has to do with the fact, it exploits the fact that the apex angle of the Giza equals the sidereal angle of the Russian.
Okay.
So anyway, I'm sorry, I'll have to show you that another time, but those are just some fun things that I've kind of put together.
That's all right. That's all right. Okay. So let's see. I'm going to share the end screen really quick. Can you stop your share really quick?
Yes, I can.
I'll override it, but
hang on. There, I did.
Okay. And then I'm just going to go. 1 second. All right. So let's just get everyone over to unpacking the problem. I'm going to try to have this up tonight. And so come Monday at 11 a.m., we're going to have Charlie Zeese on, and he's going to go over all this.
And we've recorded this one already, just to be clear. But
so are you going to be on
chronological order?
Yeah. So, but it's good to kind of go over this again because it was a really neat topic.
But yeah, give it to Charlie and also to George Leoniak. I'm sure he'll be interested.
You forward to everyone.
I will. Yeah.
All right. Good. All right. So yeah, that premiered Monday, 11 a.m. and fingers crossed, providing nothing goes wrong. But I think that's all good. All right. Well, this is where you go. And thank you, Greg.
Thank you, Jeff.
And thank you, everyone. You guys have a good one. And if you enjoy this, hit subscribe, like, or comment, please. If you have any questions, comment. I'll kind of try to be active. All right. Let me stop share. Let me show. Let me go back. All right. Do you see these? Oh, my goodness.
See y'all later.
We're new with this. All right. Take care. Have a good one.
Bye.
Thank you.